Good afternoon, sir. Good afternoon. Can we start?
Yeah.
So, good afternoon, dear participants. Good afternoon, dear participants. Now we are entering into the third session of the third day HTTP. And now we have the expert from CDAC Trivandrum, Mr. Rajesh with us, who is handling this session on high-speed reconfigurable power electronic converters. Hearty welcome, sir. It's my privilege and honor to introduce Mr. Rajesh, Joint Director of CDAC Trivandrum, to the participants of this one-week HTTP. Mr. Ajish received his BTech degree from CUSAT in 2004 and MTech in VLSI and Embedded System from CUSAT in 2008, and he is currently pursuing PhD in IISc Bangalore. He joined as a staff scientist in CDAC Trivandrum in 2008, where he is currently working as Scientist E and Joint Director in Power Electronics Group of CDAC Trivandrum. He has published several papers in international and national journals, and his area of interest include real-time digital simulation of power system and power electronics, reconfigurable computing, SOC and SOPC based control system design for power electronics, AC drives, and rolling stock application. Now I request Mr. Rajesh to start the session. Please. Sir, on your screen, right bottom, there will be a present now option. Click on that. So then full screen. Then a small window will open. Click on it. Yeah,
Okay.
yes, that's it. That's it.
Okay. Am I visible?
Yes, yes, yes.
Okay. Thank you for inviting me for this wonderful occasion. I am going to present the topic high-speed reconfigurable power electronic controllers, which deals with basically a soft processor-based control design technique for power electronic system using system SOPC or system on a programmable chip design methodology. And before we directly going into the actual topic, we will see how the processor is manufactured and what is earlier the technology what we have, right now what we have, and in future what we have. So assume we are going to design a microprocessor, and the microprocessor is nothing, it is a digital circuitry, and the digital circuitry is nothing, it contains several switches which switches either logic high or logic low. So I'm going to design a processor not with the MOS transistors and using a vacuum tube, and the processor with 1 million switching devices also. So that means there are 10 raised to 66 or 1 million switching devices in the microprocessor. So we will then deal with some technical issues. So area, assume one triode occupies an area of 5 by 5 centimeter, including some space between the adjacent tubes. Then there are total, we are going to use a 10 raised to 6 or 1 million switching devices, which means that we have a 2500 meter square area is required for the microprocessor. And I'm going to reduce this area or the 50 by 50 length and breadth. I am going to reduce with multi-layer architecture about 22 by 22 meter by using 5-layer architecture. Clearly, we can see that this is not a computer which sits on someone's lap or on the desk. So now we consider the power consumption issue. Let us assume that the one triode or one transistor in our design take 5 watt. Then the microprocessor is nothing, which is inside it. We have a lot of switching devices, and assume that half of the triodes are conducting at a time. Then the total power consumed is 0.5. That is half into we have 10 raised to 6 1 million switching device and 5 watt per triode. So what it means, so we are going to consume a power of 2.5 megawatt, which actually requires a special permission from the state electricity board. In addition, we require some special infrastructure and safety measures. Now the actual issue comes, the electric power consumed by the triode is dissipated as heat. If the heat is not received continuously, the temperature will rise, and in the best scenario, the processor will shut down. Then there is a question: how do we remove this much or 2.5 megawatt of heat from an area of 22 by 22 meter? Well, the only solution available is seal the processor and place it inside a lake. But this will create a serious challenge. Yeah, this will come. The water in the temperature will go up and destroying the aquatic life in the lake. Before it, so some environmentalist will come saying that no to computer like that. So then the only solution available is put this processor in some remote waterfalls or some remote area. Surely this is not a personal computer, it's a national facility there. And coming to the reliability aspect of the processor, what we designed right now, let T be the life of a transistor in hours. On an average, we need to, that means every T hours, one transistor is failing. So we have 10 raised to 6, 1 million switching device. So T by 10 raised to 6 is the, every T by 10 raised to 6, one transistor is failing. So we are going to assume T is equal to 10 raised to 6 hours, 1 million hours. Then we need to replace one triode every 1 hour, which means that every 24 into 7 hours, we need a maintenance department, because every 1 hour, the one transistor is failing, we need to replace that. So finally, our system will look like this. The maintenance department will be very close to the microprocessor, and the microprocessor is put inside a waterfall, and we have special electricity connection to the microprocessor. So this will be the final system. And coming to the technical issue, speed is below 1 megahertz due to parasitic and wiring capacitance and other inductance, and we have a longer development time also. And from this discussion, we can understand that the area and the size is a major constraint in designing my microcontroller or microprocessor, and power consumption should be less as possible. Reliability and the T, what I discussed earlier, the T, the number is right now in years for the new microprocessors, and speed of the microprocessor is a critical condition. And moreover, time to market. Today, if we are thinking about a design, we can see the product is available in the market next day. So the time to market criteria constraint is a very crucial condition, and the cost of the microprocessor is also very it's an important criterion in the design of a microcontroller. So this is about the processor design. Now coming to the semiconductor era, and we are going to see when the programmable chip started, because our topic is actually based on the programmable chip based technology. So in 1947 we started the transistors, whereas you can see that the CPLD or the SPLDs, that is the programmable logic devices, that started around 1968 or something like that. So from the chart, the blue line shows that actually these products was there in the market, but from the yellow, when the yellow portion comes only, people started using the device. For example, in 1968, SPLDs was there in market, but people started using that in their circuit on from 1970 onwards. Similarly for FPGAs and ASICs. So around 1984, the FPGAs was introduced, but they started using in the 1988. After 4 years later only, people started using this technology. So coming to the programmable logic devices, we have PLDs. The first programmable IC was released in 1970 in the form of PROM, and at the end of 1970, complex versions of the programmable logic devices are available, and then the ancestors were renamed to simple programmable logic devices. The thing is that the functional density or the digital circuit functional density for these type of devices was very limited. And when CPLD comes, which supports complex versions of complex Boolean functions, so the ancestor is renamed to SPLD, Simple Programmable Logic Device. And the CPLD, first CPLD was introduced in the market by Altera. Now it is Intel, taken over by Intel in 1984. It is, this CPLD is based on a CMOS and EEPROM based technology. We will see what is the technology inside a programmable logic device later. CMOS is actually for, I will just briefly give an idea right now. CMOS is for functional density and EEPROM is for biasing the programmability of the device. That we will see in detail later. So yeah, we can see that at the time we have the ASIC design technology, application specific integrated circuit design technology. But actually this ASIC supports complex Boolean function or complex circuit density. But the problem with ASIC is that once the design is frozen actually into the silicon. So which means that once there is a change in the design, we need to redesign the IC, or we need to redesign the processor from again, and we need to manufacture it from the foundry, and it will take a lot of time also, and it is also somewhat time consuming and costly processing. That when we go for ASICs. In 1980s, the situation is like that. We have PLDs, configurable, fast design and modification time is possible, but it could not support large or complex functions. Whereas we have ASICs, which supports large and complex functions, and that is expensive and time consuming, but the design is actually frozen into silicon. That is the problem. Once we have a problem in the design, okay, I need to redesign, so we need to redo all the design again, and we need to remanufacture. So people started thinking about an intermediate solution, which actually sit in the midway between ASICs, PLDs and ASICs. Then in 1984, Xilinx introduced the first FPGA in the market, which is actually CMOS and SRAM based FPGA. Now we will look into what is actually inside an FPGA. Inside an FPGA, we can see that a programmable logic block, the basic fundamental building block of an FPGA is called a programmable logic block, or PLB, which the first FPGA introduced by Xilinx actually contains a 3-input lookup table and a flip-flop or a latch, and also a multiplexer. And modern FPGA actually contains more complex versions of the PLBs, and these are simply called the basic building block is actually called PLBs, or in some other vendors it is called LEs or logic elements, whatever be the name. So the PLB actually, the structure of a PLB is more or less this. So here we have a lookup table and a multiplexer and a flip-flop, where we have the lookup table is actually a 3-input lookup table, and the output of this PLB is Y and Q. The Y is used to design combinational circuits, and Q is used to design sequential circuits because it is clocked. And this D is actually the output from some other PLBs. Maybe it is a Y from other PLB or Q from other PLB if the number of inputs is more than 3. So now we will see how the FPGA is programmed, how the inside the FPGA what exactly happening. Assume I have a Boolean function y is equal to a and b and OR of not c or complement of c. Then once we wrote a statement in the hardware description language, which is the programming language used for designing FPGA based designs. So what it is doing, the compiler will convert all this expression into a lookup table kind of structure like this, which means that with ABC, we will create all y according to this function, and the output of this y is actually loaded into the SRAM cells, and the select line of this multiplexer is actually ABC. By applying the appropriate combination of the input, the mux will actually select the output y, and that will propagate to the output. So in this way, once we wrote a statement kind of this one into an FPGA design language, Then in this way, the implementation is going. If we write one more statement just below this y, let us say u is equal to a or b, then there's another PLB, or maybe in a simple sense, we can say that another PLB is instantiated with u, the outputs of u, and ABC as the select inputs. ABC as the select inputs. Then what happened is that when we power on, both lines will execute simultaneously. So that's why the hardware description language normally called as parallel language, because all the lines in the HDL or the hardware description language executes in parallel. So in this way, the language inside an FPGA HDL language is converted into a meaningful hardware like this. So we have seen the structure of a simple PLB. This is the full structure of an FPGA. This is a very simple structure. What I is shown in this one. Complex structures are right now available. So we have different PLBs which are cascaded or connected like with the programmable interconnects. And the green one shows the IO pins. So where we can take the inputs like ABC in the earlier slide, and we can take Y as the output. Suppose our design may contain does not fit into one PLB, then we need to use another PLB also. In that case, we will invoke the programmable interconnect. So coming to the FPGA design flow, we will first see what are the things what we required. Then we will code that into HDL, and then we will do a synthesis. Synthesis means the HDL is converted into a meaningful hardware in a simple sense. And finally, we will place and route which PLBs are used in which area of the FPGA this design will fit. And finally, we will download and verify the circuit. And you can see that in a simple sense, you can see that the output of the compiler is normally 1010. So normally, some vendors are called the FPGA final configuration file as bits because it is in the form of 1010 like that. So coming to the power electronic control system design, earlier we have analog control systems. Then we moved into digital control system using DSPs and programmable logic. So of course, there is no doubt about this statement because analog control is ideally precise if the sampling time is 0. Digital control system is equivalent to analog control system if the sampling time is reduced by a considerable amount, which actually demands for high-speed processing. And coming to the processors from different vendors have their own architectures, pins, instructions, and functions. And if we, in the perspective of a student, he should familiar these for every processor. That is one of the hard tasks for a student because for one processor he should read the data sheet, its own data sheet. For another processor he should read another data sheet. Then we thought with this in mind, we thought about what if we have a processor so that the user is defining in the instructions internal modules, speed, memory, and pins. For example, the user, when he is going to use the processor, he is going to decide which pin is the PWMs, which pin is the ADC inputs, which pin is the SPI interfaces, like that. So, and also it is an obsolescence-free design. So, which means that we will come to that point in the next slide. So, for that, we actually adopted SOPC, System on a Programmable Chip-Based Design Methodology. This is nothing, building an embedded system, building a complete embedded system into a single programmable integrated circuit like FPGAs. Generally, it involves large utilization of a large FPGA. Inside, we have the processor cores, soft or hard processors, memory, RAM or ROM, intellectual property, and custom hardware blocks. That means, in a summary, we can say that all or majority of the components on a single programmable chip. Actually, we had the CDAC Trivandrum is actually having a national mission project, NAMBET. From that, we experienced some difficulties with the industries. So, for railways and defense system, their equipment life or their system life is around 10 to 30 years. In India, they will not allow to change the design for this much of years. And you can see that in processor, when you come to processor industry, the processor is obsolete within 4 to 6 years. And when we use next generation processor, then the software porting and the testing of the power electronics or power system things are somewhat again difficult. So what a solution for this is, use a soft processor IP code in the general purpose FPGA. Once the FPGA is changed, you just port the IP core into the new FPGA, and the software parties are actually fixed in that one. So, and the single chip solution, it is very difficult to find out a processor with all interface required for our application. For example, coming to the railway, for with the railway open standard, they were using a communication protocol called MVB, multifunction vehicle bus protocol. It is very difficult to find out a processor with that protocol. Make the custom protocol in as an HDL IP and to use with a CPU core. That we will come to later, how to use a CPU core for a power electronics. And a single to multi-core. Suppose at a later point of time, I realized that my processor, single core processor, will not support for the design. Then actually, then I understood that I need to use a multi-core processor for my design. Then the problem is that I need to redesign the hardware again. But the same FPGA hardware can used for single to multi-core application without any additional change in the PCB design or core or the cost. And then there will be automatically one question will comes, why this processor is having 2 to 4 years of life? Because the majority of the processor industry is focused on wireless industry, and our area, the automotive, is only about around 3.1%. And you know that the wireless industry is changing very fastly. So they were actually going to, and the VLSI designers or the manufacturers, the fab people cannot keep their fab as such. And the processor industries or the wireless industry is going with a concept that nobody is going to use a mobile phone more than 20 years. So we know that our mobile phones, after 5 years, we will switch to a new mobile phone like that. So with this concept, the wireless industry is going ahead. And also for the faster control, we can use in the FPGA based environment, we can use parallel processing. The same instance or the same IP core, we can repeat more time. And there is in FPGA design environment, we have a C2H compiler, so that suppose our application C code contains a time consuming module, which is directly the C2H compiler will directly convert the software into the software, the algorithm which is defined software into an FPGA hardware. And better time to market criteria. That means we have a same FPGA board and we have a proven CPU and IP core set. From application to application, you configure the CPU with the new IP core set and directly port into the FPGA board, so that we can meet the time to market criteria to an extent. So coming to the conventional controller design for power electronics, normally assume you take an example as an induction motor drive. So normally the induction motor or the motor control algorithm, normally we will design inside a DSP or a microcontroller as a as a software program, or as a C language or assembly language program. Then we will use an FPGA in that mode. Maybe this DSP or microcontroller does not have enough PWM channels. Then we will use an FPGA for enhancing the number of channels in the number of channels of the PWM channels, for example. And if this is an industrial drive, it needs to communicate with other drives. Then we have to use a communication board, where the communication protocol is designed either on an FPGA or a microcontroller or an application specific processor. And if we consider the resource utilization inside the FPGA, suppose inside this environment, suppose the DSP is having a CAN controller, but actually we are not using that one, then that is actually a waste for that in that application. And FPGA, we will use only 10%, and here also we will use only 20 or to 40% in that case. So what we thought about that, why can't we use the SOPC design methodology to power electronics, so that all the modules are inside the FPGA along with the soft CPU. And for example, the soft CPU, the internal modules, the peripherals of the soft CPU is actually PWM generators, motor control logic, the IG space vector modulation techniques, and the Park and Clark transformation ABC to DQ. And these modules are accessed through some custom instruction. Like if you say multiply A comma B in a normal processor, we know that there is a hardware multiplier inside the processor. And when we say move multiply A comma B, A and B values are loaded into the processor multiplier, and the next cycle we will get the output. Like that, if we read the voltage and current of the drive from using an ADC interface and load that to a motor control logic hardware actually sitting as a peripheral to the processor, so that the next cycle the processor will generate the PWM sequence and the switching pulses. Then this technique we actually used it to design the high-speed reconfigurable power electronic controller, so that the entire FPGA we used it as a controller chip. So I told you, for a railway application, suppose we need an MBB controller, the multifunction vehicle bus. That is the protocol used in the Open Railway Standard. So in that case, I told you it is very difficult to find out a processor which is having MBB, the multifunction vehicle bus interface protocol. Then the same protocol we can design as in HDL language, and we can couple that to the CPU. Then this way our design can be simplified. As an example, the motor control. Normally we will use the speed sensorless speed control. In that instead of directly measuring the speed, we will estimate the speed from the mathematical model of the motor by measuring the voltage and current, which since these are electrical quantities and it is easy to sense the voltage and current from the motor. Then we will feed that to the motor dynamic model, so that the motor dynamic model will estimate the speed, and with that speed we will generate the control application. Suppose in our processor there is a module called motor dynamic model, and input to that motor dynamic model is voltage and current. Then we can see that, like multiply A comma B in a normal processor, you just feed the voltage and current to the motor module from the CPU, and the next cycle the hardware will immediately calculate the required pulses, and which will drive the PWMs. This is the concept what we used in the high-speed reconfigurable power electronic control application. In the DSP or microcontroller application, the motor dynamic model we need to design in a C software, C language, with a more than 10 or 15 number of lines. But here we have a hardware, and you know that the hardware will perform faster than software, where the C language software will execute, or the assembly soft language will execute sequentially, whereas we can perform in a better way than software language. So this is the overall structure of the high-speed reconfigurable power electronic controller design methodology that we adopted from the SOPC methodology. We have a CPU core, and we have the power electronic components required for a particular application. For a particular application, we require PID controllers, the PWM modules, the motor dynamic model, the phase transformation, ABC to DQ, and of course, some floating point hardware also we can couple to the CPU, and some custom instruction module, filters. So in this way, we can design our own processor for our own application, and can be ported into an FPGA. Now the FPGA becomes the physical processor, and the user can assign the required the pin number according to his convenience, so that a generic board is required for handling most of his application. So for that, in CDAC Trivandrum, this is actually happened in 2013. So we designed this in we developed a generic board on Cyclone 3 FPGA, and this is actually we are using in some of our control applications for AC drives and DC drives in our office actually. So yeah, of course, we need require a peripheral interface card, which is, this is actually the custom designable, because from application to application, because the FPGA voltage level is actually 3.3 volt level, we need to scale this voltage into 12 volt to drive a actually a gate driver kind of stuff, so that we need a converter board like this. Then coming to the processor in FPGAs, so we have soft or hard process CPU cores. Soft CPU means processors which are implemented in VHDL Verilog and can be downloaded onto an FPGA hardware. Example, Neos 2 microblaze, ARM Cortex M1, RISC-V, etc. RISC-V is an architecture, and there are several versions of soft RISC-V architecture is available. And these are highly reconfigurable. That means the user can edit the CPU code and he can plug his own modules into that one, and also he can generate his own instructions for his own processor. It's a schematic or a code like software. And some of the soft processors available are Neos 2 microblaze and the OpenPython. This is actually for parallel processing, and RISC-V, that is actually based on RISC-V architecture, and Vega. In CDAC Trivandrum developed a processor which is called Vega software. Right now it is in soft format. CDAC and it is actually RISC-V architecture. It is following RISC-V architecture also. The user can edit this processor core and he can attach his own modules onto it. And hard processor means inside FPGA there is a physical processor sitting. So these are called SoC FPGAs. Normally inside the FPGA we can find out ARM Cortex processors on the FPGAs, but the only problem is that we cannot alter the pin number and other things connected to the connected to the FPGA. That is the only limitation for this hard processor, but it will perform very faster than software processor applications. So we used to prove the concept, we used Altera Neos 2 CPU earlier, and the speed of that processor is from 20 to 430 megahertz. So depending upon the FPGA what we are using. So then we will see how we can design such a reconfigurable processor system for a power electronic application. So what we have is soft CPU, which is nothing the Neos 2 kind of stuff, or the soft CPU, which are easily available from the net or from vendors. And we can use and the required peripherals for this. We can attach the required peripherals like a flash interface, JTAG UART, and system ID for some protection purpose to the soft CPU. And here we can add some power electronic specific modules to make our soft CPU as a custom processor for our own application. So here you can see that we added PWM, PI controller, timers, and ADC and DAC controller. And the protection logic is also connected to the processor bus interconnect. And the beauty of such type system is that here you can see two protection logic blocks are added here. One is actually working in conjunction with the soft CPU. One is directly working with the PWM. So in some right now the power electronics is going to silicon carbide devices where the high switching frequency is required. So suppose we need to protect our system very faster. In that case, suppose the current through an IGBT is increasing somewhat high, high level. In that case, the processor will the protection logic will interrupt the soft CPU, and the soft CPU will calculate the current value, and which will give a direction to the soft PWM to stop the PWM module to stop the firing. So in that case, we can use a protection logic directly without any conjunction to the soft CPU, and the from the ADC controller, the protection logic will continuously monitoring the current through the IGBT, and which will, when the current is increasing beyond a limit, the protection logic can directly stop the PWM. After stopping the PWM, the soft CPU will identify that okay, this protection is already happened. So with a small processor system core, we can have a wide variety of applications normally which are achieved with the high-end processors, high-end hard processors or DSP processors. So only thing is that when we design the PWM or PI controller IPs, we should always follow the bus standard of the soft CPU which we are using. So we developed some of the power electronics libraries. So we developed around 20 to 25 power electronic libraries for applications, and how to design a new IP core for a new application, and some controller cards. And actually, this for propagating this type of design, we are actually giving this to educational and academic institutes, and some of our supports also we are giving. So this is the as a summary. This is the design flow of the of a soft processor core system design. So first we will analyze the power electronic system. Then we will see what are the things which is required for the power electronic or power system. So then according to that, we will add to the soft CPU, we will add the required modules. Then we will generate do the hardware project, and the hardware output file will be directly downloaded to the FPGA. So that is the FPGA becomes our custom processor. After that, we will do the software. We need to write a software application for the custom processor. From the off-the-shelf drivers and the power electronic specific IP drivers, we will generate the application project for our power electronic application. Finally, the software project also we downloaded, compiled, and the machine language code is actually downloaded to the FPGA, so that the physical FPGA process, now the FPGA will act as a physical FPGA. Suppose in a one time you understood that, oh, okay, this is not possible, I need to add a phase transformation module also. You can add the module and rewrite this, and this in the same FPGA you can directly download that soft processor system. And the summary, the design flow is like this. As what we have a soft CPU. Upon that, we will add our off-the-shelf modules. Then we will add the power electronic specific modules which are required for our power electronic application. Upon that, we will write this application software, and using custom instruction, we can access these power electronic modules. Then coming to the custom instruction, the control blocks in the processor are handled through custom instructions or custom functions. Let us say we have a PI controller as a hardware module inside our processor. So this is a C-like structure. The functions which are going to access this PI controller in our module is hardware init PI. We need to initialize the PI with our KPKI values, or at any time we need to disable or enable our PI module. And input to the PI controller is we need to give the input with the error value, and the next cycle we can get the corrected value for doing the control purpose. You can see that only 4 instructions, and by looking at the code written by one engineer, another power electronic engineer can easily understand what he exactly doing in this project. So this is so that the number of, and you can see that the number of lines or the number overhead to the processor is actually very limited. What it needs to do, it is actually doing only a data transfer to the different hardware modules, nothing else. So that what we can, the advantage is with a cheap CPU core, we can achieve high-end processing using this type of methodology. And the advantage is good readability, number of lines are less, and faster execution. And we of course, you can visit nambet.in for getting more idea about the libraries which we developed and the design technique what we used. And around 20, right now the number is increased to 25 power electronic specific IPs are there. So depending on application, the user will first configure his processor, then he will write a soft processor based system for software upon this for this software soft core processor system, and then the whole design is ported into the FPGA. So coming to some application example, DC-DC converter control using high-speed reconfigurable power electronic controllers. Suppose we have a boost converter, and I am going to use a voltage mode control of boost converter. So what I need to do, from the block diagram, I can see that I need to read the output voltage using an ADC, and I need to feed the reference voltage. Then you do the subtraction on that one, then feed that to the PI controller, and there is a limit or the PWM module. Then the error corrected value is fed to the PWM module, and then that is given to the boost converter. In a software or the controller design perspective, what are the things, what are the steps we need to do? We need to first read the ADC voltage. Okay, we can use a simple instruction. We can define a simple instruction or a simple function for that one. ADC read. It is not like a C function. It is actually directly reading the value from the hardware. ADC read the channel number. Then subtract from the reference voltage. Then the third, PI in. Then PI out, that value, PI out, that we can connect to the PWM. So that by looking at the block diagram, the user can easily design the software, application software for the control system. Then this is, of course, we can, in the FPGA design tool, they will allow to see as a block diagram schematic of the processor what is design. Now you can see some of the pins. Now we can assign pin number for these pins in the physical FPGA hardware, so that much flexibility is there in this design. So we tested this in around 2013, this design. Initially we tested in an 8 kilowatt DC-DC converter, where with a boost converter, and at the time we used a TMS320F2812 as the processor. So it took around 6 microseconds to complete the main loop of that boost converter control at a 150 megahertz. But here you can see that 800 nanoseconds CPU clock at a 800 nanosecond to complete one time loop at a clock frequency of 100 megahertz, which means that actually the soft CPU is a small, cheap and low performance one, but we are adding the hardware modules on that soft CPU. We will make the soft CPU to do better things, so that you can see the time difference, how much time we can save in the design. So similarly, for an AC drive control, the same structure, the same block diagram. Okay, we can add an integrator to the CPU and ABC alpha beta to ABC module. Then what we need to do, from the set speed we can read from an ADC, and that value directly we can give it to integrator in one instruction. Like if the user likes another instruction, he can rename the instruction. That much flexibility we can have in this type of design. Integrator in, then we will get the theta. From this value we can the sine cos lookup table, we can have V alpha and V beta. Then that we can directly give it to the alpha beta to ABC module, which is a hardware inside the inside the FPGA, alpha beta to ABC. That value we can give it to the PWM module to create the PWM pulses for the voltage source inverter. And also we can have multi-core application on the same FPGA board with this. We can create different processor one for controlling the DC-DC boost converter, and processor 2 controls the drive part, and the processor 3, let us say processor part. So we can define different processors depending upon the FPGA resource, and which are actually, so that we can have a multi-core design on the same FPGA. So this is an example. So here we with the multi-core application, we achieved a time step of 1.5 microseconds, which is actually very less as compared to the single core application. So in this way we can save, we can partition our design in both in hardware and software, so that one physical processor on the FPGA handles the boost converter, and another processor 2 is handling the inverter. Like that we can have different cores on a single FPGA board. So we already did the same thing on a field-oriented control of induction motor. In that you can see the red blocks. The red blocks actually we designed as a peripheral to the CPU, and the other blocks we actually written in software for the CPU software. And what we got is that the main loop took only 10 microseconds in a 100 megahertz soft CPU environment, whereas in the TMS320F281214, which took around 22 microseconds in 150 megahertz. So the advantage is that the higher level of design reuse, the same FPGA board and the same IP core set we can use it for different application, and the reconfigurability is high. So of course we can reconfigure the hardware, reduced obsolescence risk. What we have, all we have, the software, sorry, the soft core CPU design and the IP core design is available to you as a text file. So once the FPGA is also obsolete, you can try the same design in a different FPGA format. Simplified design and update. Of course, from single core to multi-core, we can easily, with the same board, we can easily change. And the parallel processing, we are using the concept of parallel processing than software pipelining. Improved time to market. Yeah, at any point of time, you can change from single to multi-core. These are the design advantage of this type of design. Any doubts in this? Because we are going to a new topic.
Hello, sir. Hello.
Hello.
Yeah, actually, few doubts people asked in this regard. Can I post in your chat box now?
Yeah.
Okay. Participants were asking few doubts.
Okay.
Actually, first question came from an industry person.
Okay, sir. Why are we using rectifier then inverter for induction motor? For induction motor supply in railway, why not connecting induction motor supply to directly? Okay, because we need to achieve different speed, and we are using because the supply available is 24 kV, and we need a variable voltage when variable. We are actually using the DTC, direct torque control, or what exactly, frequency variable control. For that, they are using like that. First, we rectify that to DC, but in the inverter side, we are converting that to. We are controlling the frequency for controlling the frequency and voltage for controlling the torque and the speed of the motor. Second question: how many H-bridge circuit can be gate pulse from this CDAC design hardware? Actually, the small board, the FPGA board, is having 55 IOs, and you only need to that means up to 55 IO you can use it for PWM or other purposes. So that is the limitation for that hardware. So if the design actually you require around 55 IOs, you can use it for you can fire that much of you can use that much of PWM channels. And the only thing is you need to design your own level shifter, because the FPGA board is 3.3 volt only, and you need to design your own FPGA level shifter for converting that to 3.3 to 12 volt. That is the only limitation in that design. Is the system real time or any interface?
Yeah, Ajay sir. One more question related to the earlier question is how many ADCs it has, ADC channels.
Yeah, actually, right now FPGAs are coming with inbuilt ADCs, which means that inbuilt ADCs, we are using that inbuilt ADCs. Around the 12 channel is there, and we are using a new board which is called a Max 10 FPGA from Intel. 12 channel is there, but you can also have for some application like high speed environments, some power system quality measurement applications. In that case, you can use an external ADC, and this you can directly connect to the FPGA using SPA or any other interface. Okay, what is the isolation of PWM interface? Yeah, this actually this will give you a digital pulse in the level of 0 to 3.3 volt, and you have to use your own gate driver module. That way you like a with the galvanic isolation that you design. This is actually only a processor board, And like to another, like the case of other microcontroller design, either you have to design your own isolation, or you have to use off the shelf isolation for that thing. In our case, we used a galvanic isolation, and that we designed ourselves.
And sir, one more thing is like whether the developed board, what you are having, whether it can be interfaced with MATLAB.
Yes, MATLAB means what? That is one thing I forgot to mention you, that you can develop an IP from MATLAB, okay, and that you can directly connect it to the CPU. In that way, you can use.
Okay. Yeah, I think that's all. What program? Another one more question. What programming language is used for design?
Yeah, that is. It's like a C environment only. C direct you can use C, but here you are using your own custom functions like a PI in, PWM out, like that. But that function is not a C at the implementation level. It is not a C software. It is actually an interface to the hardware that we made. In the higher level, we made it as a C like construct.
Okay. I think that's all from the participant side.
Okay, then we will move to the recent trends in this type of designs. So you can see one board. This is parallel. This is actually from Adaptive Technology. It's a credit card size computer. You can also try this type of design in this type of boards also. And this is contains around 16 cores on 16 contains a 16 multi-core processor, and also having a single FPGA, where you can try this type of design. And surprisingly, the cost of this board is only less than 20,000 rupees Indian monies. This is only a credit card size supercomputer. Right now, 64 cores are also available. And I didn't get a question, because we have FPGAs. Then can we design the same thing? I told you in the starting itself, if we go for analog control system that is precise, can we achieve the similar way like this? A similar way FPGA, that means can we design analog circuit configurably? The answer is yes. Right now a product is coming, FPGA, field programmable analog array. The concept of switched configurable analog blocks like programmable logic blocks are available. And actually the technology started when the FPGA were introduced itself. People were started thinking about an analog cousin of FPGA, that is FPGA. And it is actually reasonable development has happened in 1991. Experimental version is released in 1995, and which is stabilized in 2005. Now this is available in the market, but the off-chip resources are still very limited when compared to FPGA. That is only limitation. Here you can have high-speed computation in analog domain itself. So that's one thing. About CDAC Thiruvananthapuram, we are basically working on electronics and electrical engineering, and we have in across country we have 14 centers. Of course, in NIT Silchar also one of our new center is there, and these are the technology available in research available in CDAC Thiruvananthapuram, Power Electronics Group, and Broadcast and Communication Group, Hardware Design Group, and the Vega processor is designed by Hardware Design Group, the Control and Instrumentation, and these are the group. And the CDAC Thiruvananthapuram is the nodal center for National Mission Technology on Power Electronics. So this much about my first presentation. I have one more presentation. Before that, we can have a thought about the Moore's law. Here you can see that the Moore's law, earlier we have a television set like this. Now we have a television set which is very slim. As I show you, a credit card size supercomputer. But what happened to us? Earlier we have some physical walking to switch on the TVs and other things. Now we just think about that one, and the products are electronic gadgets are becomes slim and we are become fat. That's the only change in. That's one interesting fact I noticed in this developments. Thank you. So shall I go to the next presentation?
Yes, sir.
So next, I will show you how to design this IPs. I told you about IPs like that. So how to design an IP for a BLDC motor control application. So we will first see how to design in hardware description language a BLDC motor control PWM generator. And finally, I will tell you about the how to interface that to the soft CPU. So this is a BLDC motor, in a simple cross-sectional view, or in a simple sense, this is a BLDC motor where we have three phases, U, V, and W. This is the starting point of U, and this is the ending point of U, like that. So all the phases are arranged in 120-degree apart, and we have a two-pole rotor. So this is nothing a permanent magnet. So here we used a Hall sensor based technology to identify the position of the rotor. So here HA means which is connected to U phase, and HB is which is placed on V phase, and HC is which is placed on W phase. When the north pole is point towards the U phase, then HA will be logic 1 and all other will be logic 0. If the north pole is in between U and V, sorry, this is actually V, U and V, then HA and HB is actually 1. In this way, this Hall sensor is working. With keeping this in mind, we will look into the PWM generation sequence for a BLDC motor. So this is the basic connections of a BLDC motor. We have an H bridge, three-phase bridge inverter, where the U phase is connected here, V phase is connected here. So all the top switches I am calling as high side U, high side V, high side W. And the bottom switches I am going to call it as low side U, low side V, and low side W. Now, so right now, the north pole is pointing towards the U phase, which means that HA is 1 and all other HB and HC are 0. Now, I want to rotate this north pole towards in anti-clockwise. What I have to do simply, see, assume that if the current is flowing to a phase, this point, then that point is north pole. If the current is leaving, that point is south pole. So now if I flow a current through the U phase and leave through U bar, then this point U becomes north pole and U bar become south pole. And I need to rotate clockwise. So that it should not come to, the rotor should not come to V bar also. So what I have to do, I need to make V bar also north pole and V as south pole. So how the current is flowing? So I need to flow current through U phase and leave the current through U bar and again enter towards V bar and leave through V. So in this way, that means when the Hall sensor position is 100, what are the switches I need to turn on? That means I need to turn on at high side U, and from U to U bar, yes, U to U bar, we need to leave through U bar and we need to enter through V bar. That means from like this, and we need to leave through this low side V and complete the circuit. So now the rotor is moved to W bar. It find a new equilibrium position. Again, I need to rotate. Now the new Hall sensor position is 110 because it is in between U and V phase, or HA and HB. Now the Hall sensor position is 110. Then again I need to switch. What I need to do? I need to make W bar also north pole. So in this way, so that what are the switches I need to switch? From through U, I need to enter the current, U bar leave the current, and W bar I need to make it as a north pole. So that through W bar enter the current and W I leave the current and coming to the source back. So that now I need to switch high side U and low side W. Then again I need to rotate. So what are the switch position, new switch position? If you do the same analysis, now you can see that I need to switch high side V, and through that high side V, then V bar, leave through V bar, enter through W bar, and leave through W, and coming back to the DC source. So in this way, we can, for the complete rotation, we can generate complete cycle. We can generate the by looking at the Hall sensor position, we can generate the PWM sequence for the we have the switching sequence for the different switches. Now, one question: can we have a Hall sensor position 111? No, 111. What it means? It means that the north pole is pointing towards HA, HB, HC, which will not happen anyway. And 000, that is also not possible because the north pole is not pointing towards any Hall sensor. If we are getting such a Hall sensor position, you declare it as a motor fault or a sensor fault. So in this way, we can have the PWM sequence. And you can interestingly note that when we switched its high side W, or when we switch high side W, now here we are switching low side U. And the next cycle we are going to switch low side V, not the high side U of this particular rank, which means that we actually in BLDC motor control we do not require the dead time control, because immediately we will not switch the once we switch the high side U, we will not switch the next cycle or the next switching pulse, we will not switch lower side U, we will switch some other pulse, some other low side of another bridge. So in this way, the dead time control is not required in BLDC motor control. And also, yeah, dead time control is actually not required. And also you can see that at any time the motor is in series with one high side and one side low side. So what we can see that we need, because this one is this one and this one are series switch in this for this motor. In this case, we need to apply the PWM pulses to control the motor. PWM pulses only to the high side, and for the entire duration of that PWM pulses, we can make the low side V as high permanently. No need to apply PWMs on the low side. So in this way, we can do we can make the PWM. So only PWM pulses we need to apply on the high side switches, and the low side switches we need to only apply the either high or low for the entire duration of the PWM. So in this way, we can see that the PWM, where depending upon the Hall sensor position, we can have the PWM generation sequence. So when 100, when the Hall sensor is 1000, we need to apply high side U, and low side V is logic high, and all other pulses are low. Like that, we can generate the PWM sequence. Now, this is the final high level block diagram of the PWM generator. So what we have, we need a carrier module, carrier generator, depending upon our switching frequency, and a reference. Of course, a reference is used for controlling the speed. Now, the PWM generator will generate the PWM. So, and we know that depending upon HA and HB, we need to either, for the high side, we need to either direct the PWM to the high side or logic 0 to the high side. And for the low side, only we need to direct, or we need to provide a path for logic 1 for low side or logic 0 for low side. In this way, we can write a selector for that. So and we can design a custom instruction for in our environment. Actually, we tried this one in this environment. We used this instructions first for an initialization of the PWM IP, and second enabling the control register, and we are applying the reference and the Hall sensor value. We will read the Hall sensor value and the speed reference to the PWM module. Directly give to the reference and Hall sensor value as the input to the PWM module. When while looking at the Hall sensor and the reference, this logic will automatically create the PWM for the BLDC. So this is the, and I will show the code so that you can have a familiarization with this. So I think everybody knows VHDL, so that you can see that this is the entity. Entity is nothing the where we are defining the input and output ports. So we define the input and output ports. And what are the things we required in this particular circuit? We need a carrier generator and a selector. That's all. So the carrier generator we can define. This is the process part of the VHDL code. The carrier generator we can define as a sequential circuit. So here I used a 2 kHz PWM frequency for the BLDC motor control and 100 megahertz clock frequency for the whole IP. So then for 2 kHz, the carrier is designed like a counter like that. As like in C, you will design counters like that. So we can define the counter, and here the comparator, this module. So this module, the comparator will come here. If the PWM reference is greater than or equal to carrier count, then the PWM is 1. And if the condition is wrong, then PWM equal to 0. And here you can see the selector. The selector is actually defined like this. Depending on the Hall sensor value, when the Hall sensor is this one, we will directly map PWM to the high side U, otherwise 0. Like that, for the low side, we will map either logic high or logic 0. And this you can have a look at. I will share this with the organizers so that you can have this one. And now, how to interface this one? Actually, I didn't put that in slide. For giving the values to this one, you take which soft CPU you are using. You take its processor bus specification. Depending on that, you just rewrite the port specification. That's all. Based on that, you can directly interface this to the your soft CPU. With this, I am going to end my presentation. I think you know the VHDL, understood the VHDL code, and I will share. You can have a look at it. Thank you.
Thank you, sir, for your highly informative presentation. Like even we people will be contacting soon for the new reconfigurable processor and everything. Okay. Yeah, it was highly informative because all the participants' comments were so good. So thank you for spending your energy and time for making such an excellent presentation. Okay.
And one thing I would like to tell you,
yeah,
the government of India actually announced one processor challenge, India microprocessor challenge.
Okay.
And you can apply for that processor challenge with some design like this or in your own way. So okay. That the soft processor designed by CDAC, IIT Madras, and I think IIT Kharagpur is also there. So you will get the hardware board and the processor core. And you just and at the end you just as freely from our ministry, so that you develop the things and show that it is having a potential. You just use it. That's all.
Okay. Yeah. So actually, this information is for the participants.
Yes.
Yeah. Then, so once again, thank you, sir, for accepting our invitation and for giving such a nice expert lecture. Thank you so much.
Okay, thank you. Thanks once again.
Okay. Okay, sir.
Can we stop the call?
Yes, sir.